Shubhabrata Das from Presidency College. He will be talking about small cancellation groups. So up to you, Shubhabrata.
Thank you. Thank you, Arpan and Shobhu, Vishnu, and others for the invitation to talk this German fest. The small cancellation theory is a pretty old one now. That the main works, I should not say main. It's started with Max Dehn's work on the surface groups and his works on the decision problems for fundamental groups of these closed orientable two surfaces. And he solved those problems, the word problem and the problem. And while solving those problems, he observed certain behavior of the presentation of the fundamental groups, and those behaviors. He used the hyperbolic metric in his deductions, but later on, I guess by Reidemeister, shown that those conclusions were not essentially dependent on the hyperbolic metric, on where the group was acting on the hyperbolic plane. So later on, these ideas were picked up by various people, and these are here are a few names like Tarkovsky, Grindlinger, Britton, Sheep, Linden, Schub, Rips, Olshanskii, and others. So Grindlinger proved a theorem which Max Dehn had proven in the surface group context. He proved in a much more general context, and there started the theory of small cancellation, I would say. So let's get started. So here we have a group G with a presentation like S, and S is the generating set. We have not mentioned finite or infinite here, but for most cases we will stick to the finite presentation. S and R both finite, and we will mention where it is not, where it is otherwise. And here by this presentation, we mean that G is generated by S. That means we have G as a quotient of the free group on these letters S, and the kernel of this quotient map, the kernel of this epimorphism is the normal subgroup, which is generated by these words. So a word is a finite string of letters, and the length of a word is the number of letters in it, and it's reduced when there are no such subwords like this. And we call these types of words in this R to be defining relators. And a relator is cyclically reduced if you apply a cyclic permutation on this relator. If you still do not have any such subwords, it is cyclically reduced, and it's symmetrized if all elements are cyclically reduced, and it has all the cyclic permutations of all R's and their inverses, and so on. Now, the most important definition here is of a piece. A piece is a word. It's a subword. A piece relative to the symmetrized set of defining relators R is a subword. Of at least two distinct elements from capital R, two distinct relators. And since we are taking things up to cyclic permutation, symmetrized R, so we can take U to be prefix in two distinct R's. If it appears in distinct ways in two distinct relators, we can choose the relators in such a way that they are the prefix. It really doesn't matter so much. So then we come to this thing called a Kampen diagram, and here we see what this diagram is. It is a compact, simply connected two complex, CW complex, which is in R2, and where each one edge, each one cell, which are edges, that will be oriented and labeled by a letter in S. See, here we have the generating set S. That means it's a symmetric generating set. We have the S letters and the S inverse letters. I mean, if we have a small s, then we have small s inverse also in this set. So this diagram, the edges, the one cells in this two-dimensional CW complex, they will be labeled by small s and small s inverses coming from this capital S. And each two cell, its boundary, it should be a word like. So R is our set of relators. So essentially, we are thinking words in R as some circles, some loops or cycles rather in this type of a diagram. So these are typically the elements of capital R. So each two cell has a boundary word lying in R. So what Van Kampen lemma talks about is that if a word is trivial, if a word in G is the quotient of the free group Fs by this by the normal subgroup generated by this subset of words. So in this quotient, if a word W is trivial, I mean, it's trivial if and only if there exists a ready Van Kampen diagram, a diagram of this type, over this presentation whose boundary word is W. So roughly how we get there is that since a word is here, is trivial in G, that means it must lie in the normal subgroup generated by R. That means it must look like a product of conjugates. So this type of balloons we can think of as product of conjugates, this being a GI, this being a RI, and this being a GI inverse. So this is the identity. I can think of it as I'm traveling via GI, I'm traveling the relator RI, and then I'm coming back to the origin by inverse. So since the word is trivial here, so it should look like this, and then it should, in the beginning, it should look like this balloons, wedged balloons. And then we can see that there are a lot of cancellations taking place here and other places. So those other places would give rise to the pieces as we see, as we'll be seeing soon. So there will be a lot of cancellations taking place here in this product, and that will give rise to such a thing. That's the content of the Van Kampen lemma. That this would give us two-dimensional CW complex like this.
I have one question.
Sorry?
So can you hear me? Yeah, so I have one question. So I'm Abhijit. So you said that this is compact, simply connected two-dimensional CW complex, right?
Yes.
Just take, say,
a trivial word. A trivial word. For a trivial word, we have this.
So you said the Van Kampen representation is compact, simply connected.
I think simply connected here is a typo.
Okay, thank you.
Simply connected here is a typo. I'm sorry, very sorry. Thank you. So simple connectedness would come from a trivial word. So yes, thank you for pointing out. Simple connectedness here is a typo. Okay, so in the next slide, we see what are known as the small cancellation conditions. So there are a few variants of small cancellation conditions. The most used or known ones are the metric small cancellation conditions, which is the following: that if G has a presentation like this presentation satisfies a small cancellation condition C prime lambda for a lambda greater than 0 is is when each piece must be contained in a relator. So this is the relator R where the piece U is contained. So whenever U is a piece, the length of the piece U should be less than lambda times the length of the relator. U is a subword. Okay, so that is the small cancellation condition C prime lambda, and we can see here for an example. This is the tessellation given by the presentation of genus 2 surface, a closed closed orientable genus 2 surface, and the relator here is the product of two commutators AB, commutator AB and commutator CD. So it's a one relator group. Now we can see here, these are the only possible pieces, right? So, a piece is, we call some subword a piece when two such relators, they come together on some subword, where two relators overlap. The boundary of those disks overlap. So here we can see in this example that they can overlap only along either A or B or C or D and so on, right? So the length of this word is 8 and the length of this is 1. Sorry. Length of this is 1 and so clearly this presentation satisfies small cancellation condition C prime 1 by 7. Okay, so this is known as the metric small cancellation. Now there is another small cancellation condition called CP for P natural number. Here, what it essentially, the definition says that the presentation SR is satisfying small cancellation CP if no element in the set of relators is a product of less than P pieces. At least, the relator not be a product of less than P pieces. Okay, so that means there should at least be P subwords, P segments on the cycle, if we can think of it. Then there should be at least P segments on the cycle where any other relator overlap with the given one, with any given one. So that is the meaning of this condition CP, and this picture somewhat captures that if you have a relator which is R naught here, there should be at least P pieces here. Okay, so here it can be more as well. So this presentation again, the previous one, it satisfies cancellation condition C8. It was a C prime. It was a C prime 1 by 7. Here it's a C8 presentation. The same thing. This is a C8 presentation, as we can see very clearly. The pieces are only the generating letters. And from the definition, we can very well observe easily that a C prime 1 by n condition would imply that it C of n plus 1, Cn plus 1. So that's obvious because any piece has to be less than 1 nth of the relator. So there has to be at least n plus 1 pieces to give you a product, to give you a relator as a product. Okay, so there is a next condition which is called a TQ condition, and we won't be using this condition, especially the TQ condition, much in this survey. But still, for the sake of completeness, this is a condition. The definition itself doesn't look very obvious, but you see here that if you have L relators, L at least 3. The presentation satisfies TQ if you have less than Q relators, greater than 3, greater than or equal. Then, if consecutive elements, consecutive elements in this set, they are not inverses of each. Don't cancel off. One doesn't cancel off the next one. So when you form a product, so in that, if you take the products, then at least one of them is reduced without cancellation. So if it satisfies TQ, and you are taking L of them, not Q, I mean something less than Q. So here the meaning of it is reduced without cancellation. That means they don't have any such overlap like this. So if you take a bouquet like this of relators, and then if you have less than Q of them at a point, then at least one such product, these consecutive products, which is reduced without any cancellation, right? So you can just think of removing this one, and in that case there will be these two whose product will you will get cancellation. So this condition essentially means that so this is part of a Van Kampen diagram. This vertex is an interior vertex of the Van Kampen diagram. So essentially, this condition tells us that if the presentation satisfies this condition, then at any interior vertex there should be at least Q. There should be at least Q of these relators, giving us the degree of any interior vertex being at least Q. So we can think of the presentation of the free abelian group of rank 2. There we can see that the presentation would satisfy both C4 and T4. You can think of it just looking at the dual graph. I mean, you just take the points corresponding to join an age and so on, and that would give you, I mean, the TQ condition. Okay, so here are a few examples. So this satisfies the C4 T4 condition, and as we have seen that for a genus G or genus G surface, the defining relator is a product of G commutators. So we have a 4G one relator with length 4G, and still here the pieces are only AI inverses, BIs and their inverses. So they are all one length 1 pieces. So it satisfies C prime 1 by 4G minus 1. So this is a theorem by Pride, where he proves that this is C twice N group and so on. And this group, you can see in this presentation that the only pieces are AIs, not the squares, because the squares do not appear in two different ways. Only AIs appear in two different ways, so they are the pieces. So they two relators can overlap. So they are the pieces. So here it satisfies 1 minus 1. And here we can see another presentation like this. This is a very typical small cancellation word. AB square, AB cubed, and so on to AB 100. You can just calculate, check the length of this, and check which subwords can be. So you should find subwords which appears in two distinct ways. So here you can see a subword b to the I a b to the I plus 1. You get this subword here once, and again in this b to the I plus 1 a b to the I plus 2, you can find the same subword again sitting inside this string b to the I plus 1 a b to the I plus 2. So you take the b to the I, the second, the last part, and then a here, and then you take the first b to the I plus 1 from this b to the I plus 2. So you get this subword appearing at least one time. So pieces are of that type. So what would be the largest piece of that type? So you will find a b to the 99 a here, b to the 98 here, and you can see the pieces there of the form b to the I a, b to the I plus 1, and then you have also b to the i's as pieces. So you can calculate that the pieces are at least they're less than 1/20th of the length of the relator. So here is a very nice example of a small cancellation group. It's a very nice paper written by Rips in 1982. That given any finitely presented group G, and positive, you can find a small cancellation group. This group is a small cancellation group. It's a finitely presented small cancellation. So given any finitely presented group, you can find a small cancellation group here, so that G, the given group, is a quotient of this small cancellation group. And not only that, you can also, you have a control over this coefficient, over the small cancellation coefficient. So you can also choose that. I mean, the proof, the detail of the proof would tell you that you have a control. You can simply use words like this. You can use words like this to construct such presentations here, so that it satisfies small cancellation condition like C prime lambda. How do we, I mean, the outline of the proof, how do we get that kind of a group? So if G's presentation is like this, then we would generate H with the same generating elements, N, and two other extra elements, and then define, as I was mentioning, then define relators involving these, so that the relators would satisfy a condition like this. That would give H to be a small cancellation group. You define a homomorphism from H to G, you just send AI to AI and BJs to 1. And the kernel would be exactly B1 by B1 and B2, and that's this finitely generated kernel. So this is a very nice example where that given any finitely presented group, we can and a real number, positive real number, we can construct a cancellation group of that coefficient of that order, so that G is a quotient of that small cancellation group, and that too with a finitely generated kernel. So that's a very nice construction. So it's a very small paper. It's a good read. Now, now we would look at the decision problems, the so-called decision problems, through which Max Dehn started off the study of this type of groups. So, what are the decision problems? I mean, but here the two problems I would mention is word problem, which is to decide whether or not a given word is trivial. Conjugacy problem, which is about deciding whether or not two given words are conjugate in the given group G. So these two problems then prove that for fundamental groups of genus G surfaces, these problems have a solution. I mean, these problems are solvable. I mean, solvable in the sense that we can design an algorithm. He devised an algorithm that is essentially based on his observation, his following observation, which would give these problems, a decision, an answer in finite time. So how is that? The observation he made is that a freely reduced non-trivial word W, if a freely reduced non-trivial word W in this group, this fundamental group, is trivial, then W contains more than half of a defining relator R. It contains more than half of a defining relator R. So the defining relator here is the which is the product of these G commutators. And he's saying that if a reduced word, any freely reduced non-trivial word, has to be trivial, then it should contain more than half of a defining relator. that's the single relator here, or any cyclic permutation of R inverse here. So this observation led to the famous Dehn's algorithm, and later on Grindlinger extended this observation. He proved similar results in the C prime 1/6 groups, and later he proved for C prime 1/8 groups the conjugacy problem and so on. So this paved the way for the decision problems, the solvability of the decision problems in small cancellation groups. So then what the Grindlinger says is that it's supposedly the most remarkable result in this small cancellation theory. Not only in the classical small cancellation theory, in the various other forms of generalizations that small cancellation theory has. In every small cancellation type theory, there would appear something like a Grindlinger lemma in a different avatar, maybe, but that's a crucial result. So what the Grindlinger lemma says is that if W be a cyclically reduced word in a small cancellation group, G satisfying a small cancellation hypothesis C prime 1/6, represents a trivial element, then this subword U, which is also a subword of a defining relator. So this was not a defining relator, this was just a trivial element in G. That means it's an element here in the normal subgroup generated by this set. Now, this says that if it's trivial, then it has a subword U, which is also a subword of a defining relator, such that it's a subword, this is a prefix, the rest of it is V, and it is a subword in this way, that length of U is more than length of V. It's length of U is greater than half of R. So U is at least half of the defining relator. So that's what Dehn observed in surface groups. And which later on proved by Reidmeister that it doesn't necessarily depend on the hyperbolic metric structure and so on. That's the motivation for Grindlinger proving this result in this. So in the due course we will mostly look at this type of metric small cancellations. We will also see some CP type small cancellation conditions in the coming slides. So now, based on this Grindlinger's lemma, what is the Dehn's algorithm? This is the algorithm for the word problem, and the algorithm for the conjugacy problem would be a little different, but it will reduce to this one. And there you have to conjugacy problem is to determine whether or not two given words are conjugates. So it can be shown that those two words will represent a Van Kampen diagram which is like an annulus, and whose boundaries are the given two words W1 and W2. And it can be shown that one can find a path along that annulus and cut it open, cut the annulus open along that, and that would give rise to a simply connected Van Kampen diagram, and that would reduce the problem to the word problem and so on. So how to solve the word problem, the Dehn's algorithm in this context of a C prime 1/6 groups? What this algorithm says is that first you search for such subwords from defining relators R, which is of this form. You find this kind of subwords. If you replace that subword by the inverse of this, because this is smaller. If you replace this by the inverse of this, why the inverse of this? Because U and V, UV is 1, would be V inverse. So you are replacing U by V inverse. Now V inverse has the same length as V. So essentially what you are doing is you are reducing the length of W by replacing it with V inverse. And after replacing, it says that you freely reduce. If you have again something like S inverse, you replace it with empty words and so on. You continue. So call it W1. In G, the word not and W1, these are equivalent, as it can be seen easily. And the W1 is lesser than W0, the starting word. So we have got an equivalent in this presentation, which gives me the same element in the group, and with a smaller word length. Now you keep constructing inductively. You keep constructing such words by repeated application of these two. Search them if you find place with them, and then freely reduce and get the word W1. This way you keep constructing W1, W2, and so on. And these will be equivalent by the same argument in G. And each of them would be the, if you can pass to a further word, further Wi plus 1, its length would be smaller than Wi. So at most W number of steps would lead us to either an empty word. So that would tell us that W is a trivial word. And if it doesn't, it would lead us to a word W hat, which cannot be shortened by this method any further. And then it means that it is not one in the group G, because this is the way you reduce in a group. So it cannot be further reduced in this presentation. So it's a non-trivial word. So this is the Dehn's algorithm in short. So a lot of combinatorics is involved behind these statements. The Green-Linger lemma implies that in a C prime 1 group, you have something like this, right? That you have a subword which is like this. So then that means you can run the Dehn's algorithm, right? So in C prime 1/6 groups, you have a solvable word via this Dehn's algorithm. So this was a very nice result in the classical small cancellation theory, and this was later improved, generalized, extended to many different contexts. Next is the linear isoparymetric inequality. So we have a freely reduced W0, which is in the set of relators. And we can define a combinatorial area. We can count the number of two cells in the Kampen diagram. We have seen that it is too complex, and we can just count the number of two cells in the diagram. That's the area. So the length of the perimeter. This is the Kampen diagram. Then this is the perimeter, and the length of the perimeter, since the Van Kampen's lemma says that the perimeter delta M0 is W0, so the length of the perimeter is just the W0 norm of W0, the word length. So the presentation satisfies a linear isoparymetric inequality, means that you have a constant C such that a freely reduced relator W0 can be a boundary level of a diagram M0 with at most these many two cells. At most these many two cells it can fit in that Van Kampen diagram. So that's that tells us that and in another consequence of this green lemma is that these C prime 1/6 groups, they satisfy this linear isoparymetric inequality. And now we see that in the previous talk, Dr. Shadhar talked about hyperbolic groups, and hyperbolic groups were defined by Gromov, and there were many different characterizations for hyperbolic groups, and one of them is a linear isoparymetric inequality. So, and C prime 1/6 groups, they do satisfy this linear isoparymetric inequality. So here is a definition of hyperbolic groups. In the previous lecture also we have seen this. So in this from this result, which is a consequence of Green-Linger's lemma, we see that it has a linear isoparymetric inequality, and that implies that C prime 1/6 groups are hyperbolic groups in the sense of Gromov. So historically also these small cancellation groups played an important role in the motivation behind these groups. So now the main question becomes the guiding question becomes that if we are given a group G and subgroups R1, R2, Rn, what should be the conditions that we should put on this collection of subgroups so that we understand the normal subgroup generated by these subgroups of G and the quotient of G by this normal subgroup generated by R1 by Ri's. So I mean, let's just rephrase it. Then we will see that S was a generating set. So we have seen that G was a quotient of S by the normal subgroup generated by R. And what is this R? So R was the collection of words, right? Words in certain types of words, reduced, etc., in Fs, but they were words. So the normal subgroup generated by R can be thought of as the normal subgroup generated by the cyclic subgroups of these words. If we have to think of the small cancellation condition in this context of the statement, that how do we put conditions on general collection of subgroups, a small cancellation like conditions, so that we understand the normal subgroups and the quotients better in general. So the classical small cancellation theory would fit into this setup as this, that here the free group and our I's are these cyclics, infinite cyclics. So in this context, I mentioned here that Mikhail Gromov, he mentions in one of his very important papers, Random Walks in Random Groups, that freedom of G, freedom in the sense of this freedom, G is free, right, in the classical small cancellation. He mentions that the freedom of G is not indispensable, in the sense that I mean, you can relax the freeness of Fs and look for similar small cancellation conditions. So what would be the next step to look? If we dispense with the freeness, if we relax the freeness, that in some free group, which are the word hyperbolic groups. So then comes the generalization of small cancellation theory over the hyperbolic groups. So this generalization was by Olshanskii, and Olshanskii was working on small cancellation theory for a long time, and he also constructed the Tarski monster group, and he extended the small cancellation theory on hyperbolic groups, in this sense that in any way, if we have to define the small cancellation, then we have to somehow say that a piece, first we have to fix the notion of a piece, and then we have to say that a piece, whenever it appears in a relator, it is small compared to the relator, the length of the relator. that means the small cancellation. When we form a product, it cancels less subword compared to the total length of the product and so on. So we have to somehow come to a definition of a. We have to somehow get hold of something like a piece. If we do not have a piece a priori, then define something like some generalization of a piece to make sense of this discussion. And here, Olshanskii's prescription is that you start with a hyperbolic group, which is G naught, which has this generating set S and relators R naught. Now, in the sense of the previous slide, so here you find something like a R1, that a symmetric set of geodesic words. Excuse me. In G naught, where each of the words are at least of some length, some very large positive number, greater than a large positive number. So we are not going into the details of these choices, this construction, but intuitively we will see why it is a generalization of the earlier small cancellation theory. See, earlier when we defined a piece, this is a typical situation from a classical small cancellation theory. A piece is a subword of a relator where two different relators meet. So this is a relator. In this description, U fits somewhere. This is another relator. In its expression, U fits somewhere else. So there is a piece where two relators overlap on their boundary, on the relator along subwords. So now Olshanskii is suggesting that we will be taking a quotient. We will be taking a quotient of G naught by the normal subgroup generated by R1, and that is like G1 is generated by the same thing S, and relators are more. It's R1, are not union. Now, an epsilon piece with respect to R1, an epsilon piece is something like this. Here, some subword of R1 words, like R and R prime, we will call an epsilon piece. U is an epsilon piece if it appears in R1 word like this. There should be another R1 word, which is R prime, where we have another something like this U prime, which gives us something like a quadrilateral here, where the two vertical sides of the quadrilateral is very small, is epsilon. It's very small compared to the size of the relators and also the hyperbolicity constants of the base group and so on. So we are not going into the choices of these coefficients. So here we will call such a subword to be an epsilon piece, and we will say that R1 satisfies a small cancellation condition C prime epsilon rho lambda. Earlier we were not mentioning epsilon and rho. This epsilon and rho are the coefficients coming for the fact that we are no longer on a free group quotient situation. So here, just see that compared to the lengths of these relators, the previous stage relators, which are coming from R naught, can be very small. So there would be large overlaps. Long overlaps with the R1 relators of R naught relators, possibly. So we want to avoid that. So we are looking only at R1 words, and R1 satisfies this small cancellation condition if an epsilon piece is less than lambda times this. Okay. So now moving forward, the small cancellation theorem in this context by Olshanskii, it says that for suitable choice of these coefficients epsilon, rho, and lambda, the quotient is delta 1 hyperbolic for some delta 1. Here it was delta not hyperbolic, and the hyperbolicity constant changes, and we have a delta 1. Okay, so now I just mentioned here quickly that this can be repeated. just from the construction, from the definition, it is very obvious that this process can be repeated. We can take a quotient, further quotient of G1 and so on. Okay, now another approach to small cancellation over hyperbolic groups is given by Delzin, and Delzin's approach was by using Gromov inner product to define a small cancellation condition. And in his definition, he took a G which is hyperbolic, and he took a set of relators which are suitably symmetrized. I'm not going into the detail. Some suitably reduced elements in G, which we will be considering as relators, and we choose lambda to be less than 1/8. Then we say that R satisfies the small cancellation C prime lambda if the minimum of all elements here, the minimum length of all elements here are greater than this. And you see that this is something like that row condition in the previous. And here, he doesn't talk essentially about a piece, but what he talks about is possibly far more penetrating, in the sense that he talks about something called a fellow traveling condition, in the sense that R1 and R2 are elements here, and for A, where A's length is bounded above by 1000 delta, some constant, then A R1, and this is the Gromov inner product. This is just the definition is that A, B, and C, if this is the thing, then this measures essentially how much a geodesic starting from C going to A and B fellow travel. In a free group, this is very easy to see. In general, we have an estimate for we have a definition of the Gromov hyperbolic groups in terms of this inner products. And here he enforces that whenever that fellow traveling distance is greater than something, for these two elements here in capital R, then this relator, if we can say it, if we can call it a relator, then this relator R2, since its fellow traveling with AR1 is quite high, greater than some number, then R2 has to be a conjugate of R1 by A. So that's his definition of small cancellation. He says that the group G would, the set R would satisfy the small cancellation condition C prime lambda over the hyperbolic group G, delta hyperbolic group G, if it satisfies these. And then he uses this condition to show that whenever we have a non-elementary delta hyperbolic group G, and then if R is a family of suitably chosen words, elements in G, satisfying such a small cancellation condition, then the normal subgroup generated by R is free. That's remarkable. And then also he shows that the normal subgroup, the quotient of the group by the normal subgroup is delta prime hyperbolic for some delta prime. And here is a special case of that, in the sense that if we take something called hyperbolic elements in hyperbolic groups, a set of them, F1 to Fn, with large something called stable length or stable norm something, we will see a similar definition a few slides later. Then the normal subgroup generated by them raised to an index n, then there exists such an integer n, so that if we raise all of them to n and then take a normal subgroup generated by them, then that is free. And also similarly the quotient is hyperbolic. So these are remarkable results.
Shubhabrata?
Yes.
Yeah. So could you wrap up another 5 or 6 minutes?
Okay, sure. I will speed up. So
Sure.
another result in this paper, very important result, is Askew University, which says that given any countable group, there is a quotient of the given group where you can embed that given group. So he proved the Askew University for groups satisfying this type of conditions. In fact, he proves for non-elementary hyperbolic groups Askew University, which was also proven by Olshanskii in a different result by different methods. And then comes the graded small cancellation. As I mentioned earlier, that this process of Olshanskii's small cancellation and also Delza's can be repeated. So it's nothing but a repetition. We start with a G naught, and then you keep considering small cancellation subsets with different coefficients, and then keep taking quotients that will give you a sequence of epimorphisms, and the limit of this is called a graded small cancellation group, which is like a stratified small cancellation. Not one coefficient holds for the entire group. You stratify the relator, and they satisfy different small cancellation conditions. And another is a very important notion of graphical small cancellation by Gromov, where he considers graphs and graph maps, labeled graphs and graph maps, and defines small cancellations. What he says here is that if you take a bouquet of k circles, which I call rows k, and then the fundamental group of that is the free group, and if the circles are labeled by S letters, if you have something called a label, something called a map like this from any graph with certain condition to this bouquet of circles, then you can consider this quotient group of the free group by the induced map and the normal subgroup generated by that, and you can define a small cancellation condition on that, and he proves that quotients of such groups will be hyperbolic again, like this. The group GM is hyperbolic, and theta m, the initial graph index in the Cayley graph of GM. These were actually elaborated by Delza and Olshanskii in a later paper. So from graphical to geometric small cancellation, I'm out of time. So this is just one step further from the previous thing, and here you see there is a new way of defining small cancellation over groups acting on hyperbolic spaces in a certain way. So I will not go into details here. And there are other generalizations of small cancellation theory, one by Damani, Girardel, and Osin, the important one, rotating families and so on. That's also motivated by Gromov's work, and also Coulomb. So these results have very important consequences, and this is then filling was proved by Osin for relatively hyperbolic groups. SQ universality was proven. So another thing is cubical small cancellations, and there are plenty of different applications like Dehn algorithm, then filling, and normal subgroups in FIM hyperbolic, relatively hyperbolic, mapping class groups out FNs. These are coming from the generalized geometric small cancellation context, SQ universality, and other construction of monsters like this. Gromov's monster, I just want to mention, is a very important example. This is a counter example, the first one, and now possibly there is one more example where you have a group which does not coarsely embed in a Hilbert space, which gives a counter example to some version of a Baum-Kohn conjecture. Okay, so I will stop here. Thank you.
Thank you very much, Shubhabrata, for this nice presentation.